TiO2. A few years later, the photolysis of water by TiO2 was reported, which really formed the basis for a lot of research on TiO2. This was the electrochemical splitting of water using TiO2, as well as in the presence of UV light. Around 1977, there was a report on cyanide decomposition by TiO2. And then in the 1980s, there were reports on immobilization of TiO2 on supports. Obviously, this was motivated by the photochemical effect of TiO2 on a number of application areas, and it stimulated a lot of research on TiO2. And then from around the 1990s, moving forward, there was a lot of research on the use of UV as well as visible light for activation of TiO2, a lot of research on modification of TiO2 in order to enhance its activity. And then a lot of new photocatalysts were also reported, some of them as single component and others as heterogeneous kind of components. So this whole trend shows how this field has been developing from the pre-1950s up to the current state where we are. In my next slide, I show the exponential growth in the field, where I highlight the number of publications on Scopus per year, on photocatalysis plus titania, and photocatalysis plus carbon nitride. What you see there is quite an interesting trend where there is a huge exponential growth in research on photocatalysis. And then from the around 2000 moving forward, you see a growth and almost a stable kind of scenario in the research on photocatalysis and titania. And then from around the 2014, we see emergence of a new material, which is carbon nitride, which is also a photocatalyst. So this mix shows quite an interesting scenario where photocatalysis is really growing in terms of research, but you see that there is a change now where not only titania, but other photocatalysts are being used, and titania is still so much used in this photocatalysis space. And then you also see emergence of new photocatalysts such as carbon nitride. So what spares this kind of research interest? Obviously, since these are photocatalysts, we are looking at the use of the visible and infrared region of the electromagnetic spectrum, where we have the UV component contributing about 6%, the visible component about 44%, and the infrared almost 50%. Obviously, there is an increase, a reduction in the energy of the photons as we move from the UV region to the infrared region. And then on the right, I show some of the common photocatalysts or semiconductors that are used in this process, their valence band as well as their conduction bands. This is very important in the selection of the photocatalyst for a preferred application. So the application of your photocatalyst is determined by the band positions in terms of the valence band as well as the conduction band, depending on whether you want to carry out a reduction process or you want to carry out an oxidation process. Preferably, the conduction band and the valence band should be at an appropriate position to be able to carry out the desired kind of reaction. Here, I just show the basic principles of photocatalysis using a single component photocatalyst. So you have absorption of light, exciting the electrons from the valence band to the conduction band. This results in the formation of photogenerated electron hole pairs, and then the migration and recombination of these photogenerated charge carriers. And then we have adsorption of reactants and desorption of products on the surface of the semiconductor photocatalyst. And then we have the redox reactions taking place on the surface of the photocatalyst. These reactions can either be oxidation reactions or they can be reduction reactions. As I mentioned earlier on, this is based on the position of the valence band as well as the position of the conduction band. So this is just the basic principles of photocatalysis. So what has been done is that these basic single component photocatalysts have got their drawbacks and challenges, some of which are the fast recombination of the generated charge carriers, also the use of UV radiation, which is quite expensive. And then we also have the issue of activation of these photoconductors by using visible light. So there are a lot of issues to deal with the traditional photocatalysts that researchers are trying to solve. They are trying to look at ways of improving the performance, the efficiency of these photocatalysts. Some of these techniques include metal deposition. So metal deposition on a traditional photocatalyst, forming composites with other photocatalysts, anchoring dyes on the surface of a photocatalyst, doping and co-doping with metals and nanometals, also surface adsorbents, attaching molecules on the surface of a photocatalyst, and then forming hybrids with other materials. This is quite common these days, where researchers are looking at nanometal kind of materials and then attaching them to these semiconductor photocatalysts in order to improve a lot of these physical chemical properties of these photocatalysts. So I'm going to look at some of these processes or some of these techniques that are used to enhance the performance of the traditional semiconductor photocatalysts, so that we come up with new kind of photocatalysts with enhanced properties, with desirable properties for a particular application. So one of these techniques is doping, and doping simply means adding another element to an intrinsic lattice. A very good example is the addition of phosphorus to silicon, or addition of boron to silicon, which is the traditional semiconductor kind of lattice. So you can form the N-type semiconductor if you have donor impurity which contributes free electrons. So if you substitute the silicon atom with a donor that contributes free electrons, then we end up with an N-type kind of semiconductor. And then if you substitute an atom in the lattice with an element that you have got an electron deficiency, then you end up with a P-type semiconductor. So we now have different classes of these semiconductors, where you have the N-type semiconductors and the P-type semiconductors, depending on the type of dopant that is added to these semiconductors. So what is the importance of doping in semiconductor photocatalysis? One of the major benefits of doping is reducing the band gap. So a lot of work has been done on adding or doping semiconductors with nanometal dopants, such as nitrogen, carbon, boron, in order to replace some oxygen sites on the TiO2. This has resulted in the formation of some hybridization between the nitrogen 2p orbitals and the oxygen 2p orbitals. And this results in intra-band gap states in which there is a reduction in the band gap. And reduction in the band gap is very important in photocatalysis in the sense that you can shift the absorption edge of the resulting doped material from the UV region to the visible region. In the process, you can use visible light to activate this kind of material. So this is quite important, and it has resulted in a lot of research work where people are looking at introducing a single element, introducing two elements at the same time, introducing even more than two elements to result in a mount-doped kind of semiconductor. The doping types, there are basically two types of doping, the substitutional doping as well as the interstitial doping. So in the substitutional doping, you are substituting a particular element in the lattice with another one. And then in interstitial doping, we are forming some states, intra-band gap states between the valence band of the semiconductor and the conduction band of that particular semiconductor. I'll be looking at some of the challenges that we encountered in trying to determine the actual type of doping that will have happened in a semiconductor as you try to substitute an element in an intrinsic semiconductor. And then we also have metal deposition, which is done to deposit a metal on the surface of a semiconductor. This has been shown to slow down the electron-hole recombination rate through addition of these metal dopants that act as metal sinks. So the whole idea is to trap the electrons that are photogenerated during excitation of the semiconductor. In the process, you increase the lifetime of the holes to perform the oxidation reaction through generation of the hydroxyl radicals, which would then degrade some of these organic pollutants. And then we also have an interesting kind of modification where you form nanocomposites or hybrids with other materials. And this has also been shown to slow down the rate of electron-hole recombination through anchoring of these kind of supports that act as electron sinks. And a very good example is the use of carbon nanotubes. Carbon nanotubes have got a dual advantage in the sense that they are very good at adsorbance. They have a very high surface area, and therefore you can absorb the pollutants on the carbon nanotube because of the high surface area. At the same time, they have a very good electron mobility ability, and therefore they can channel the photogenerated electrons from the semiconductor through their pi electron systems. And in that process, again, you enhance the lifetime of the holes in order to generate the OH radicals, which are used for oxidation of the organic pollutants in water. So this slide is just showing some of the mechanisms of the enhancement of the photo efficiency when we have a combination of a semiconductor, probably TiO2 and carbon nanotubes, where the carbon nanotubes can act as electron sinks for the photogenerated electrons, and then they can act as photosensitizers because they are very good at absorption material in the entire UV region. And then they can also act as impurities through the formation of Ti or carbon bonds. And in that process, you form intra-band gap kind of states where you have a reduction in the band gap of the semiconductor. So they play quite a significant number of roles in enhancing the photodegradation of the pollutants when attached to semiconductor photocatalysts. And what are the synthesis routes for some of these materials? Quite a number of them. the choice of a particular synthesis route is determined by the overall morphology and the sizes of the nanoparticles that you want to generate. Sometimes it's also availability of resources in the particular institution. You know, some of these techniques are complicated, others are quite cheap and affordable, and they can easily be performed in a general laboratory. And then I'll move on to now to the new type of photocatalysts that are currently being produced by many researchers, which I'm calling the hot pipelines. So these include the formation of heterojunctions, the formation of what are called the Z-scheme photocatalysts, the S-scheme photocatalysts, as well as the double Z-scheme kinds of photocatalysts. So these are kind of systems where you have, instead of a single component semiconductor photocatalyst, you now have maybe 2 photocatalysts, you have maybe 3 or even 4 components combined together through a suitable synthesis method. And then you look at how you can manipulate the charge carrier movement in these type of systems. The whole idea is to enhance the separation of charge carriers, enhance the visible light activity of these materials, and then also sometimes you want to look at improved morphology and sizes of these materials to be able to perform a particular function in water or wastewater treatment. So under heterogeneous photocatalysts, we have quite a number of them. We have the conventional heterojunctions where you just pick 2 semiconductors and then you combine them. You have the PN heterojunctions where you are combining a P-type semiconductor with an N-type semiconductor. And then we have the surface heterojunctions where you're looking at specific surface of that particular semiconductor and then look at how different surfaces can interact in order to enhance the electron charge separation. And then, of course, we have the semiconductor carbon kind of heterojunctions where you have a metallic metal type semiconductor with a non-metal material in order to form a heterojunction that can still perform the function of reducing electron-hole recombination. So under the heterojunctions, we have 3 types of these heterojunctions. We have the type 1 heterojunction, which is also called the straddling gap kind of heterojunction, where you have interface between 2 different semiconductors with unequal band structures, which results in band alignment. So for the type 1, the conduction band and the valence band of the semiconductor A are respectively higher and lower than the corresponding bands of semiconductor 2. So again, you're looking at the band positions of the 2 semiconductors, semiconductor A and semiconductor 2. Can there be any movement of charges from semiconductor A to semiconductor B, or the movement of holes upon irradiation from semiconductor A to semiconductor B? Very unlikely, and therefore there is poor separation of electron hole charges or the charge carriers, because whatever is coming from A to B will combine with the holes in the semiconductor B. So there is very poor separation of electrons and holes in the straddling type 1 kind of heterojunctions. And then we have the type 2 heterojunctions, which are called the staggered gap type. In this type of heterojunction, you look at the position of the valence band and the conduction bands of the semiconductor A and semiconductor B. You select these in such a way that the valence bands are close together, and then the conduction bands are also close together. So upon contact, you're going to have the electrons moving from semiconductor A to semiconductor B, and then the holes moving from valence band B to valence band A. And this will result in spatial separation of charge carriers, because as the electrons now have a longer path to move from A to B, and the holes also moving from B to A, you have that extended lifetime of the charge carriers to perform the oxidation reactions as well as the reduction reactions. The major drawback of these kind of systems is the competition between electron hole separation and recombination. What it means is, whilst the idea is to have that spatial separation of charge carriers, you can still have recombination of electrons and holes, either in semiconductor A or in semiconductor B. So the efficiency in terms of degradation of these pollutants is limited in this kind of system, even though some progress has been reported, and actually type 2 heterojunction is the most common type of these heterojunction kind of photocatalysts. And then we have the type 3 heterojunction, which is called the broken gap. So in this type, there's poor selection of the semiconductors where the band positions do not match at all. So the gap is broken, and then electron hole migration and separation between the two semiconductors cannot occur. So in the process, there is no enhancement in the efficiency of the photocatalyst in such kind of systems. And then we have the PN kind of heterojunction. In the PN, you have a P-type semiconductor next to an N-type semiconductor. So upon irradiation of this kind of heterojunctions, you form a charge, an internal electric charge at the interface of the two semiconductors, the P-type as well as the N-type. And that interface is very important in channeling electrons from the conduction band towards that charge separation, that charge region, or movement of holes from the semiconductor N to that particular region. So the whole idea is you're going to have enhancement of the charge separation, because electrons that are generated in the P-type will eventually move to semiconductor B in that particular region where we have the electric field, and then electrons generated in the holes that are generated in the N-type semiconductor will also be channeled towards that electric field. And in the process, you have sufficient separation of electrons and holes. So the electron hole separation efficiency in the PN kind of heterojunction is faster than the type 2 heterojunction due to that synergy between the internal electric field and the band alignment between the P-type and the N-type semiconductor. And then we have the surface heterojunction, which can form the type 2 kind of heterojunctions, where you have specific surfaces within the semiconductor. It could be the 001 surface, it could be 101 surface in the TiO2, resulting in channeling of electrons from one surface to another, and also channeling of holes from one surface to another, resulting in the formation of a stochastic barrier or a stochastic junction that will result in delayed electron hole recombination and therefore increase the efficiency in the degradation. And then the semiconductor carbon kind of heterojunctions. This is the use of other materials such as carbon nanotubes, materials such as graphene, carbon nitride. We have seen a lot of work on carbon quantum dots being formed together with semiconductor photocatalysts. So the whole idea again is to improve the charge carrier separation, also enhance the surface area of the resulting photocatalyst, and also shifting the absorption to the visible region. These are just some examples of tin oxide and carbon nanotubes. We have titanium dioxide and graphene heterojunctions where the electrons can be channeled to these carbon materials, and in the process reduce electron hole recombination and enhance the photoactivity. And then I'll move on to the Z-scheme kind of photocatalyst. Here I'm just showing the evolution timeline for these kind of materials, which the first generation reported around 1979, where we have liquid phase Z-scheme. And then as time went on, we had the second generation around 2006 for all solid state kind of Z-scheme. And then we have the third generation around 2013, where we had the direct Z-scheme kind of at least being reported. So there's a progression in the different kinds of Z-scheme photocatalysts that are being developed with time. And then this graph is just showing the trend in terms of the reported research on photocatalytic as well as Z-scheme. You can see that Z-scheme kind of photocatalysts are also showing an exponential growth with time from as far back as the 1979. And you can see that around the 2014, 2016, there's a huge increase in the number of publications on Z-scheme kind of photocatalysts. What drove this kind of scheme? It's inspired by the biomimetic artificial photosynthesis, where you have a Z-scheme kind of electron channeling between photosystem 2 and photosystem 1. And therefore, this idea was also developed in heterojunction photocatalysts. So we have different types of these Z-scheme photocatalysts. We have the redox mediator type Z-scheme photocatalyst, and then we have the direct Z-scheme photocatalyst. The difference between the two is that in the mediator type, you have a donor-acceptor kind of material that can be used to accept electrons or holes, or it can also donate electrons and holes. And then in the direct Z-scheme, upon irradiation with light, you have movement of electrons from the conduction band of one of the photocatalysts to the valence band of the photocatalyst. This will enhance the lifetime of the holes for oxidation and the lifetime of the electrons for reduction, though the movement of electrons from photosystem 1 to photosystem 2 through the bending cannot be ruled out in such kind of material. So the mediators can be metal particles. They can also be carbon materials in the mediator type kind of Z-scheme photocatalyst. And then we have this S-scheme. So the S-scheme consists of a reduction photocatalyst and the oxidation photocatalyst. Very similar to the type 2 kind of heterojunctions. The only difference here is the bending type in S-scheme does not allow electrons to flow from one of the photocatalysts to the other, and therefore you have only electrons and holes combining in the form of an S kind of system at the interface. So the bending type in this kind of photocatalyst will allow the electrons that are generated in the reduction photocatalyst to remain there, whilst the holes that are generated in the oxidation photocatalyst to remain there. The only charge carriers that will combine are the electrons in the conduction band of the oxidation photocatalyst and the holes in the valence band of the reduction photocatalyst. So in that process, you again have extended lifetime of the electrons in the reduction photocatalyst and then the holes in the oxidation photocatalyst to drive these reactions. So this is just an explanation of those processes. So you have more electrons on the reduction photocatalyst for reduction reactions and more holes for the oxidation reactions. And then we have another generation of Z-scheme photocatalysts that emerged recently. These are called the dual or the double Z-scheme kind of photocatalysts. These are a bit more complex than the type 2, the Z and the S-scheme systems. And it is important that the selection of the semiconductor photocatalyst will result in a reduction in the recombination of charge carriers. Also, you need to look at the Fermi levels and the band positions so that you get the desired overall effect. So in these kind of systems, you have a ternary kind of system where you have three kind of photocatalysts. You select them based on their valence band and conduction band positions. If you want a reduction kind of a reaction, then you need to make sure that one of those semiconductors have got a very high reducing power. And then if you want an oxidation kind of system, then you have to make sure that one of the semiconductors out of those three has got a very high oxidation potential valence band so that you can drive the oxidation reactions. Right, this is another example just showing the double Z scheme kind of photocatalyst. What is really a problem in these kind of systems is understanding the charge carrier migration mechanisms in these type of complicated systems. So whilst there are a lot of reports that are emerging now on double Z scheme photocatalysts, the actual charge carrier transport mechanism is not fully understood. The actual kinetics of the charge carriers within this ternary kind of structure are still not understood, though there are reports of enhancement in the photo efficiency of these systems through Z scheme kind of electronic transitions. And the band positions can be determined from experimental data through determining the electronegativity of the semiconductors, determining the band gaps of the photocatalysts, and then also looking at the band positions of the valence band or the conduction band in order to facilitate either the oxidation reaction or the reduction reaction. So we have done a lot of work on a number of these kind of photocatalysts, which I'm calling new kind of photocatalysts for water treatment, including doping, non-metal, metal doping, multi-element doping, type 2 kind of heterojunctions, semiconductor carbon kind of heterojunctions, PN heterojunctions, Z scheme, as well as the dual Z scheme kind of heterojunctions. But what you observe in all these research reports is that we rarely go to very, to the very high degradation efficiency where you get to 100% degradation of these pollutants. You still go to higher values, but still not really 100% removal of the pollutants in these kind of systems. There is also an advantage in the sense that we can use visible light to activate these semiconductors. So what is the way forward? So the way forward is based on the designs for potential large-scale application of these kind of photocatalysts. I got this picture from the work by Stephanie Loeb and colleagues, where they were looking at what could be the actual technologies that can be used to package this kind of photocatalysts for large-scale application. And they came up with 4 types of potential large-scale application systems, where they look at the slurry of the photocatalyst, where you need a membrane to then remove and recycle the photocatalyst, fluidized media, where you support the photocatalyst on a porous substrate, and then you have your light there, and then you pass your water through the system. And then you have the membrane kind of system where you have a flat sheet of membrane, and then you attach your photocatalyst to that membrane, or you embed it inside the membrane, and then you allow the polluted water to pass through, and then the optical or the electrospan kind of fiber, where you again attach these photocatalysts on a fiber, and then you irradiate the fiber and allow the water to pass through. What is the biggest challenge in these kind of designs is the lifetime of the polluted water in contact with the photocatalyst. Photocatalysis is not, it's a longer process, it takes time for this degradation to take place. But when you have the water flowing through in flow-through systems like these ones, then you may need to recycle this water several times before you get any appreciable amount of degradation of the photocatalyst. So what are the challenges? There are a lot of challenges in the design of new photocatalysts. I got this cartoon again from these researchers where they were looking at the laboratory for study on the future of photocatalysts. A lot of issues still need to be looked at. The quantum yield, the cost, the selectivity, the visible light absorption, the physical robustness of these things, reactor engineering, stability, reducing the recombination. So there are a lot of issues that are still needed to be optimized, that still need to be understood, especially in the very new kind of photocatalyst based on dual Z scheme kind of photocatalyst. So choice and selection of the semiconductor photocatalyst couples or constituents, very, very important. Poor understanding of the charge transfer dynamics or kinetics in doped or heterojunction photocatalyst. We need tools to verify the type of transitions that occur in these kind of materials. We look at cost versus efficiency. In a ternary semiconductor dual Z scheme type, for example, you have 3 different photocatalysts that you are bringing together. How does that compare to the efficiency of this particular photocatalyst? So you need to strike a good balance between cost and efficiency. And then currently there are very few. I haven't come across any large-scale practical application of these new kind of photocatalysts compared to the conventional advanced oxidation processes, where there are a lot of research reports on large-scale application of oxidants for the degradation of various kinds of pollutants. And then another issue is toxicity of these engineered nanomaterials, where there are potential risk and toxicology on human health as well as the environment. So should we continue producing these kind of photocatalysts, what will be the impact on the environment? Another challenge is complete mineralization has not been realized in the vast majority of application studies. There is still need for post-treatment. There is still need for further processes to polish and get very clean water, especially for drinking purposes. And then on future directions, I think there is need for agreed guidelines on the figures of merit in photocatalysis. What really is important in photocatalysis? Is it the material? Is it how we understand the charge carrier kinetics? Is it the efficiency that we get? Is it the use of visible light compared to UV light? So all those issues need to be interrogated so that we come up with guidelines, strict guidelines on what are the figures of merit in photocatalysis. There is a need for proper design of immobilized photocatalytic systems for large-scale application. And then we need to narrow the gap between industrial needs and academic research. And then there is also a possibility of coupling photocatalysis with other technologies, maybe incorporate photocatalysis as one of the steps in already existing water or wastewater treatment processes. And finally, I just want to highlight this scheme that I also took from Stephanie, very interesting, where they were looking at photocatalysis, whether it's sunrise, whether it's sunset, or what, they don't specify. So they look at this as the sun at the horizon. So when you see the sun at the horizon, you don't know whether it's rising or it's actually setting. But there is, in photocatalysis, there was a positive hype, a lot of work, we can see it, right? Of inflated expectation. And then normally people have doubts that is this going to work, or we're just pursuing something that does not show any potential application. And then we reach a trough of disillusionment where we are not so clear on what we want. And the only way is to progress towards niche applications and practical expectations so that people can really understand and value what these non-photocatalysts can do to solve our global problems. And then in conclusion, I'll just have one statement. When will photocatalysis for water treatment become a reality and not just a chimera? Thank you very much. I'll end there.
Thank you so much, Professor Alex, for such an insightful talk. We still have time for a couple of questions. So at this point, I will invite colleagues to pose some questions for Professor Alex. And if you can't, you can also drop some of your questions through the chat. We'll then be able to read them. Thank you. I can see there is a hand. I'll recognize Amal. You can go ahead and ask your question. Amal, you can go ahead and ask your question. While we are waiting for Amal, there is a comment in the chat box. It says, Professor Alex, thank you for such an informative presentation. Can you please elaborate on the methods of electrospinning for photocatalyst doping, since the method is generally adopted for fibers or membrane production using melt polymers?
Okay, thank you very much for that question. From the way I understand the electrospinning process, what you are trying to achieve there is the supporting the particular photocatalyst on a membrane substrate. So you electrospin in order to get very high surface area of these fibers, and then obviously the higher the surface area, the better in terms of your pollutant absorption. However, the challenge is when the particles are trapped right inside the nanofiber, then they may not be accessible to your polluted water, and there is also the challenge of shielding of the light by the membrane phase of your fiber. So there's still a lot of challenges on the incorporation of these photocatalysts into nanofibers. However, some work has been done on that, and people have reported some progress in terms of irradiating those nanofibers in order to get some enhancement in terms of photocatalysis. The main advantage is that you won't need a post treatment process, because all your photocatalysts are trapped inside the fibers. Thank you.
Okay, no, thank you so much, Professor Alex. Another question from the chat. It says, could you please indicate how it could be determined if it is interstitial or substitutional doping? So how do you tell if you have substitutional or interstitial doping?
Yeah, a very interesting question. So actually, the selection of the dopant normally tells you whether it's going to be substitutional or interstitial. So whatever you are trying to substitute, like for example, the atomic radii of the element that you are trying to substitute, when it is almost similar to the atomic radii of the element that you are doping into that particular space, then you have substitutional kind of doping. But if the size of the dopant is completely different from the size of the element that you are trying to substitute, then you end up with interstitial kind of dopant. But you can look at this through maybe XPS, do some XPS and see the kind of interaction between the elements, which is if you are looking at TiO2, for example, what is the interaction between the oxygen and the dopant that you are introducing into this particular photocatalyst. So it's still a challenge actually, but it's based on the selection of the dopant that you want to introduce into your semiconductor.
Okay, no, thank you so much for that. Amal, let me recognize you once again. I hope now we can hear you.
Can you hear me now?
Yes. Go ahead and ask a question.
Firstly, I want to thank the professor for his nice presentation. In fact, I worked a lot on the photocatalysis for organic pollutant removal during my PhD study, published in the good journals. So I usually ask myself, how can I apply this technology in the real application? So I'm asking if there is any research has been done on the combination of photocatalysis and membrane technology for wastewater reuse, for example, for agriculture reuse, or maybe wastewater reuse for drinking purposes, or yes, something like that. So there are any research papers has been done on this topic?
Okay, thank you very much, Amal, for the question. Actually, there is work on integrated technologies where people are trying to look at how to integrate photocatalysis with other techniques such as membrane technology. So what happens is you are coupling photocatalysis with the membrane technology. But there are a lot of different designs that have been reported in the coupling of photocatalysis with membrane technology. What kind of membrane? Do you need the photocatalyst inside the membrane, or you want the photocatalytic component to occur on its own, and then after that, you release the water to the membrane component so that you can now have a membrane as a polishing step for the water that will have undergone a photocatalysis. So there are quite a lot of different designs of the integrated photocatalysis with membrane technology.
Okay, no, thank you so much, Professor. I think I'll just read one last question from the chat box. How do you measure the band gap experimentally? But the question was actually instrumentally. How do you measure the band gap instrumentally?
Okay, thank you for that question. So for you to determine the band gap of the semiconductor, you then need to do some data plotting from your UVVs analysis. So you analyze the semiconductor using solid state UVVs, and then from the data that you generate from the UVVs analysis, you can then plot what are called the talc plots, and then from the talc plots, you can estimate the band gap of your photocatalyst. Another technique that I also know about is the use of XPS, where you run the XPS of the material, and then on the lower binding energy scale of your XPS spectra, you look at how you can extrapolate that to the to the intensity axis, so that you get the band gap of the particular material. So those are the two techniques that I know for estimation of the band gap of the semiconductor. I know people, some researchers use the simple inspection of the UVV spectrum to say, where are you getting the absorption edge, and then you just extrapolate that to your wavelength axis, and then you estimate the band gap, though there are a lot of reservations about that particular method of estimating the band gap.
I think in the interest of time, I'll hold it right here. Thank you so much, Professor Alex. I think if there are any questions in the chat box, you can always check it out and then give some responses. And thank you everyone for joining in this webinar. Professor Luigi has indicated that he had to rush to another meeting, so he is not here. So thank you so much, everyone.
Thank you very much.